Okay, we're going to continue talking about exponential growth and decay in 6.2, but now we're going to talk a little bit more, rather than graphing them, we're going to talk about writing the equations for exponential growth and decay. So let's talk about the difference between growth and decay in terms of definition. So the definition of exponential growth is when a quantity increases by the same factor over equal intervals of time. So let's write that down. It's when a quantity increases by the same factor over equal intervals of time. Exponential decay, it's basically the same definition, and if you want to save yourself some time here, it's the same definition except for instead of the word increases, you could probably guess this, it's decreases. So I'm just going to write ditto, and I'm going to change that word to decreases for down here. Everything else is the same. So basically the definition for exponential decay then would be when a quantity decreases by the same factor over equal intervals of time. So then let's take a look at our exponential growth and decay functions. These are kind of hard to see, so if you can't read it, you might want to make sure you write this down or listen carefully. So my first function is y equals a, and a stands for, and it's labeled as the initial amount, and then parentheses 1 plus r, r standing for the rate of growth, and this is important, in decimal form. And then that exponent is a t, which stands for time. Notice how that whole 1 plus r part is the growth factor. So that's different than the rate of growth. It's going to be important that we know that these are different. The rate of growth is r in decimal form. The growth factor is 1 plus r. So that's going to be important. And then the exponential decay function is y equals a times 1 minus r to the t power. So again, if you can't read those, you might want to write them down maybe up here or wherever you have some extra space so that you know you can read those, because we're going to need those. We're going to use those a lot in this section and as we move forward. These are exponential growth and decay functions. A times 1 plus r to the t and a times 1 minus r to the t. So if I'm going to write an exponential function, first I'm going to have to decide if it's growth or decay. That'll determine which of these two formulas I'll use. Once I've determined which of these to use, I'm going to find three things. A, the initial amount, r, the growth rate, and t, the amount of time. So let's take a look at my first example here. The first example says the inaugural means first, attendance of an annual music festival is 150,000. The attendance, y, increases by 8% each year. So aside from the fact that in our directions it says write an exponential growth function, there's a way we can identify that this is growth, okay? We have to kind of use some context clues here. It says the attendance increases, goes up, gets bigger. Those are all growth terms. So we know this is going to be exponential growth. That being said, I'm going to use y equals a times 1 plus r to the t power. Since I know that's going to be the function I'm going to be using off to the side here, I'm going to write a equals, r equals, and t equals, and I'm going to try to fill in those. So it says the inaugural attendance, that means the initial amount is 150,000. So my a is 150,000. My rate is 8%. The rate is always what it's going up or down by. It's going up by 8%. The issue here is that I said this back when I was looking at the formula, it needs to be in decimal form, so I actually have to change that to 0.08. To change a, and you could write this down if you think you'll forget, to go from a percent to a decimal, you either move the decimal place over to the left two, or you divide by 100. You'll get the same result regardless. So that's how I got the decimal, 0.08. And then lastly, my t. In this case, t is just t because we're just writing a function for t years. So we don't actually know a time yet. I think we will in the next part, but for right now, t is just t. So my equation will be y equals 150,000 times 1 plus 0.08 to the t power. Now, right now, there's not a lot of simplifying I can do because order of operations says I would have to do parentheses first. That I can do. Then I would have to do the exponent, which I can't because I don't know the exponent. So the only thing I can actually simplify right now is this part. And that's really important not to multiply the 150,000 because that would be going against order of operations. So I'll leave the 150,000. I'll simplify this to 1.08. I'll leave the t. That's my function. And that's all I can simplify right now. If I knew the t, I could go further and solve and all that. So now, I think in the next part, in part B, it says how many people will attend the festival in the 5th year. So now we're talking about 5th years. We're talking about t being 5. So I'll use my equation. Y equals 150,000 times 1.08, and t will be 5. So I'll put a 5 up there, and I can solve this. So 2 things. You can do this on your own. Well, I probably not going to do this math in your head, but if you're going to do it step by step, make sure you do order of operations, do the exponent first, then multiply. If you type this all in your calculator, it'll give you the correct answer. Don't forget to get to the 5th power. You choose the button that looks like that on your calculator, and then you would do the 5th power. So you'll end up getting y equals 204,073. It does say round to the nearest thousandth, so we would cut it off at 204,000. So my answer would be about 204,000 people attended. I am going to be picky about labeling 204,000 people. I want to know, what are we talking about? Are we talking about people? Are we talking about money? Are we talking about years? What are you talking about? I want you to label it. So make sure as you're doing these types of problems, you're labeling them so we know what we're actually answering. So let's go ahead and take a look at the next two. On the next two, we're actually going to write functions. We're just going to decide whether or not it's exponential growth, decay, or neither. So if it's an exponential function, that means it has to be multiplying by the same thing over equal intervals of time. If we're multiplying by something that is greater than 1, if it's going up, it's growth. If we're multiplying by something less than 1, then it's decay. So basically, if the numbers are going down, it's probably decay. So I do notice that as my x's go up here by 1, which would be equal intervals of time, I do notice that my y's are going down. So I'm expecting this to be decay. I want to figure out what is the factor they're going down by. It looks like if I wanted to get to from 270 to 90, I'd multiply by 1/3. 90 to 130 is 1/3, and 30 to 10 is 1/3. So this is exponential decay. Same thing on the next one. Let's go ahead and take a look at that. First, I'm going to check equal intervals of time. I have +1 here, +1 here, +1 here, and I'll check these. 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40. We are going, it isn't increasing by the same factor because it's going up. This one is exponential growth. So at some point, we're going to be able to tell the difference between is it linear or exponential, and then if it is exponential, is it growth or decay? So you'll have to know how to do all of those things as we move into the next chapter. So that's how we tell if it's growth or decay based on a table. Go ahead and turn the page. In this example, we're going to tell if it's growth or decay by looking at the function and then identify the rate of change. So maybe worth writing down, we talked about this back in 6.1, but you might want to write it down. Remember, our exponential function is this, y equals a times b to the x. That's just our function. We went a little bit further when we talked about our growth and decay, but that's an exponential function. And we talked about this back in 6.1, that if b is greater than 1, it's exponential growth. And if b is between 0 and 1, so a fraction less than 1, then it's decay. So deciding if this is growth or decay is going to be looking at that b. That b also represents my growth or decay factor. And I'm going to use that factor to find the percent rate of change. So there's a difference between factor and rate here, and that's going to be important. So let's start with example 1 here. I'm going to first identify what is b. b is always whatever the exponent is attached to, in this case 1.7. 1.7 is greater than 1, so right off the bat I can identify that it's growth. That's the easy part, or should be the easy part. Finding the percent rate of change is taking that factor, 1.07, and setting it equal to either 1 plus r or 1 minus r. So think to yourself, when will I use 1 plus r and when will I use 1 minus r? 1 plus r is for when it's growth. 1 minus r is when it's decay. So in this case, because it is exponential growth, I'm going to set this equal to 1 plus r, and I'm going to solve for r because that's what I'm trying to find, rate. The rate of change would be r. I'll solve for that by subtracting 1 on both sides. I'll get 0.07 equals r. I have solved for r, but I want the percent rate of change to go from a percent to a decimal. You're going to multiply by 100. So r is 7%. So same thing, let's try the next one. I'm going to identify what is the b in my exponential function. That's 0.98. 0.98, although close to 1, is less than 1. It is between 0 and 1, so that is going to be decay. Since this is exponential decay, that means I will use 1 minus r, and I'll set 1 minus r equal to 0.98. Careful when you solve this, it's just a teeny tiny bit more involved. I'll still subtract the 1 from both sides, and I'll end up with negative r equals negative 0.02. Obviously, I want r to be by itself, so I have to divide by negative 1. So I'll end up with r equals 0.02. Again, I need to convert that to a percent. That's going to be 2%. Remember, percents would be moving the decimal 2 or multiplying by 100, whichever way you want to remember it. My percent rate of change is 2%. So we should be able to now write exponential functions for growth and decay, tell if a function is exponential growth or decay based on the table, and tell if it's growth or decay based on an equation. Let's take a look at the last couple problems then on here. It says write a function that best represents the following situations. So keep in mind that the functions we learned, you should have them written on your previous page, are those y equals a times 1 plus r to the t, or y equals a times 1 minus r to the t. So I have to decide if it's going to be growth or decay. That's going to be my first step. So let's take a look at this first one. It says sales of 5,000 increase by 75% each year. So I see the word increase. That should tell me I'm going to use exponential growth. So I'm going to use y equals a times 1 plus r to the t. A, r, and t are what I need to find. It does say write a function, and then I'm solving for 4 years. So I'm going to write a function first with t, and then eventually I'll plug in t as 4. So I'm going to use t right away, just write a function for t years. A is my initial amount, which is the $5,000. And then my rate is 75%. Don't forget, we have to change that to a decimal, which is 0.75. So now let's go ahead and fill in my function. Y equals 5,000 times 1 plus 0.75 to the t power. Again, the only part I can simplify right now is that part in the parentheses. So it's 5,000 times 1.75 to the t power. That's my function. So I wrote a function. And then it says to find the sales after 4 years. So now I'll go ahead and plug in 4 for t, and I'll evaluate 5,000 times 1.75 to the 4th power. Again, if you type that on your calculator, it'll do the order of operations for you, and you don't have to worry about it, so that's exciting. So let's go ahead and type that in. I want you guys to actually follow along, so if you're just like, oh, I'll just wait till she's done, why don't you actually grab your calculator and type it in now to make sure you get the same thing. I got 46,894. We're talking about money, so I'll round to 2 decimal places, 0.53. So that's 46,894.53. Let's go ahead and take a look at the next example. Same thing, a $25,000 car decreases by value 12% each year. Decreases, there's my red flag. It's going to be decay, so that's a times 1 minus r to the t. Let's go ahead and find a, r, and t. A is 25,000. R is 12%, or 12%, which is 0.12. And I'll just leave t as time. Eventually it will be 10, though. So my function will be, oops, not A. A is 25,000 times 1 minus 0.12 to the, oops, sorry, I'll leave that as t right now and just simplify it. So all I can do right now is simplify the 1 minus 0.12. So it'll be y equals 25,000 times 0.88 to the t power. That's my function. And then I'll make t 10. So that's 25,000 times, oops, 0.88 to the 10th power. And I'll go ahead and type that in, 25,000 times 0.88 to the 10th power. You should be getting $6,962.52 for that one. I want you to go ahead and try these last two on your own. So pause it right here, try these last two, and then press play and follow along and see if you got them. So pause it here, try these last two, and then follow along and see if you got them. So here's what we should be getting for these last two. I'm going to put the answers on here. You should just kind of be following along, listening, seeing that this is what you got. I see decreases, so I know it's decay. My A is 150,000. My R is 0.2, and I'll leave T as T again. So that'll be Y equals 150,000 times 1 minus 0.2 to the T power. So that'll be 150,000 times 0.8 to the T, and then I'll plug in 150,000 times 0.8 to the 7th power, and that I will solve for 150,000 times 0.8 to the 7th power. Our number of birds will be about, we're talking about number of birds, so let's round to the nearest whole number now. 31,457. We don't want 0.28 of a bird, so let's leave that. And our last one, a population of 19,000 increases by 10.5% each year. Increases means I'll use my growth, exponential growth. I'll go ahead and plug in A equals R equals T. A is 19,000. R is 10.5%. Don't forget you still have to move the decimal, so that's 0.105. And T will be T. So my equation will be 19,000 times 1 plus 0.105 to the T power. So that's 19,000 times 1.105 to the T power. And again, I'll make T this time 15. And I'll plug that in 19,000 times 1.105 to the 15th power. You should be getting a population of 84,955. We'll round up to the nearest whole number because we're talking about people. Oh, I made a big stink about how we need to label them, and then I didn't label the last one. Birds. Notice that I did label the two above that because I put my $sign, so those are labels. So although I want to give you one more problem, even though it's not in your notes, it's going to be, and this is going to be on the homework, so it's going to be worth trying this. It's going to be a different formula, so you can just put this on the back side or like someplace else. There's one more formula I want to teach you, so let's take a look at that. So the last thing I want you to do, and I want you to write this someplace in your packet, is for compound interest. You're going to use this formula anytime you see the words compounded interest. The formula is, and write this down, y equals capital P times 1 plus the fraction r over n to the nt power. P stands for the principal or initial amount, just like it did before. I think I spelled initial wrong. Let me go back. Let's try that again. Initial amount. R, just like it did before, is the rate, just like it was before, in a decimal form. N is new. N is the number of times interest is compounded per year. So let's just talk about this for a second. If I say interest is compounded annually, how many times a year is that? How many times a year is annually? It's once a year, so n would be 1. If I say it's compounded monthly, how many times a year is monthly? It's 12 months in a year, so it would be 12, so n would be 12. If I'd say it's compounded quarterly is a little bit tricky. Think about the word quarter. 4 quarters in a dollar, 4 quarters in a game. That would be 4 times a year. So n is the number of times it's compounded in it. And then t stands for the time, and it has to be the time in years. So we're not going to do a practice problem on this, but make sure you write down that formula, and you're going to practice this in big ideas. If you have any questions about it, write it down, but I want you to try it. I think you can do it without having to see any examples. So write the formula down and try some of those. At the very least, just give them your best shot, and we can talk about them in class next time. So make sure you have all these notes, and then when you're done with this, go try the big ideas.